Now let's focus our attentions on weak acids. So let's take a look at one weak acid, HNO2. Okay, so if we're going to write an equilibrium expression for HNO2 in water, we take HNO2, react it with water. That's going to be in equilibrium with H3O plus, okay, and then NO2 minus. Okay, if we're going to write if we were to write an equilibrium expression for this reaction, what that would look like, Kc, that would be the concentration of H3O plus times the concentration of NO2 minus divided by the concentration of HNO2 times concentration of water. Now, I said in a previous video that the concentration of water does not change, so we can't include that. But it turns out that if we multiply both sides by the concentration of water, okay, so what we're going to do is get the concentration of water out of our expression on the left-hand side. If we take the equilibrium constant and multiply it by the concentration of water, that actually gives us a new expression, a new equilibrium expression, which we call Ka. And Ka is the acid dissociation constant. Okay, so let me make a note here. Acid dissociation constant. All right. So when we write about, going forward, when we're talking about acids and bases, we're going to express everything in terms of Ka, the acid dissociation constant, and as well as Kb, the base dissociation constant, or acid ionization constant, base ionization constant. So it pretty much means the same thing. So this would be the Ka expression for this acid. I'm going to rewrite it over here just to be clear. So the acid dissociation constant would be the concentration of H3O plus times the concentration of NO2 minus divided by the concentration of HNO2. Okay, now HNO2 is a weak acid, so that we can say that its Ka value, the Ka value is going to be very, very small, much less than 1. Now, keep in mind that we need to keep an eye on what the Ka values are. Okay, and here's the reason why. If the Ka value is less than 1, then we know that the reaction favors reactants. If the Ka is greater than 1, it favors products. And if the Ka is equal to 1, that's at equilibrium. It's also a good rule of thumb to keep in mind when we're talking about equilibrium constants back in the last chapter. Okay. Now, what we're looking at here, this table, we saw a similar table a couple videos ago. What this is doing is showing us the acid, and then also what's important for us right now, the Ka. Okay. There's also an expression where we can find something called pKa, where pKa, if we take the negative log of the acid dissociation constant, that gives us something called pKa. What we're going to do is focus on one of these weak acids. So let's talk about ascorbic acid or vitamin C. The Ka value for ascorbic acid is 8.0 times 10 to the minus fifth. So let's consider this just as just to walk through the process of what this would look like. Okay, so we're going to consider vitamin C. Instead of writing out ascorbic acid or draw the structure, we're going to write it as HVC, vitamin C, and then H means acidic form. All right. So if we're going to write the expression, the equation for this, ascorbic acid, vitamin C, reacts with water and is in equilibrium with, you can guess it, H3O plus And you're going to have Vc minus. Vitamin C, the ascorbate ion. All right. Now, if we're going to write the equilibrium expression, it's specifically asking for Kc this time. So let's write the normal Kc expression. So that's going to be the concentration of the products, H3O plus, times the concentration of ascorbate ion, divided by concentration of ascorbic acid, HVC, times the concentration of water. Now, we said that the concentration of water is constant, and if we multiply both sides by vitamin C, by the concentration of water, that gives us our Ka expression. So the acid ionization or dissociation constant would give us concentration of H3O plus times the concentration of ascorbate ion divided by the concentration of ascorbic acid. Okay. All right, so there we go. Now here's our problem. A 0.20 molar solution of vitamin C has a pH of 2.40. What is the concentration of H3O plus? All right, so that's what we need to find out. Okay, so there's a couple ways that we could go about this. All right, there's a couple ways that we could go about this. So we know that the pH is 2.40. What is the concentration of H3O plus? Well, if we remember that one way is if we know the concentration of H2O plus and we know the pH, if we're solving for the concentration of H2O plus and we know the pH, 10 raised to the negative pH will give us that concentration. So if we take 10 raised to the negative 2.40, that should give us a number of 0.00398 molar. Okay. All right, so now it says, use this information and an ice table to find the Ka of the acid and compare it to table 15.2. So what it's asking us to do is to take this equation, the vitamin C breaking down in water, and let's find out what concentrations we have at equilibrium. And this value that we just calculated, this 0.00398, that's going to be the value of the acid in water, value of H3O plus at equilibrium. All right, so what I'm going to do is rewrite the equation again. Okay, so here's my equation. So initially, I know we have 0.20 molar concentration of ascorbic acid, and the rest of these are at 0. We know that the change, it's going to have to go down. We know that we're going to make 0.00398 molar, which I'm going to, because it's so close, and this number, it's already out to 3,000, you're going to have a concentration in the thousands place. What I'm going to do is round this. Let's call this 0.0040. You can definitely tell I just woke up. But anyhow, we're going to call this 0.0040 molar, just to keep things a little bit neater. Okay, so we know that the concentration of H3O plus has to go up by that much, because that's what the concentration is. Okay, so if concentration of H3O plus goes up that much, the concentration of ascorbate ion also has to go up that much. Okay, which means that the concentration of ascorbate acid has to go down by that much. So it's going to go down by 0.0040 molar as well. All right, so at equilibrium, the concentration of ascorbic acid is going to be 0.2 minus 0.0040, which is going to give us a concentration of 0.196 molar. Okay, so the ascorbic acid does not go down all that much. Concentration of H3O plus is going to be 0.0040 molar, and the concentration of ascorbate ion is going to be 0.0040 molar. All right, so now that we have our concentrations, we also know what the Ka expression is. We just pop our values in. So again, that the expression is concentration of H3O plus times the ascorbate ion divided by the concentration of ascorbate acid. Okay, so popping in our values, concentration of H3O plus was 0.0040 molar times the concentration of ascorbate ion, which is again 0.0040 molar, divided by the concentration of the acid, 0.196 molar. Okay. And then if you multiply these two, 0.0040 times itself, and then divide that by 0.196, the value I got was 8.09 times 10 to the minus fifth. So comparing that to the value that we got, we're pretty close. So we're getting pretty much 8.1 times 10 to the minus fifth. This table has 8.0 times 10 to the minus fifth. So it's a very comparable value. Okay. All right. So what if we get the pH from a Ka? Okay. So let's try this. Let's take a look at this problem. We want to get the pH from a Ka expression. Okay. And so we need to figure out the pH of a 0.40 molar solution of vitamin C. So there's two different equilibria at play. So you've got the first one, which is the reaction we talked about before. Okay. So you got vitamin C reacting with water, and that's going to be in equilibrium with H3O plus and ascorbate ion. Okay. So we talked about this, and then we said we measured this Ka expression. In the table, it's 8.0 times 10 to the minus fifth. Okay. So that's one reaction at play. We also have another reaction since this is occurring in aqueous solution. You're going to have water reacting with water. Okay. And I apologize. I put aqueous. I'm used to writing that. So it's going to be liquid. So H2O is in equilibrium to form H3O plus and OH minus. Okay. And that expression, that Kw, is going to be 1.0 times 10 to the minus 14th. So we have two different equilibria at play. Both of them are, taking a look at the two reactions. The Ka over here for the acid is the bigger value of the two. So this is the one that we have to we're really concerning ourselves with. Okay. But the second reaction is important because it does produce hydroxide ion, which we do need. Okay. So how many different species are involved in these two reactions? You've got vitamin C, you've got water, you've got hydronium ion, you got ascorbate ion, so that's 4, and then you've got hydroxide ion. So you've got 5 different species that are in play. Which one is the more important of the reaction? It's actually the Ka, because it's much higher than the Kw, as I said. All right, so what can we conclude from this? Even though both reactions produce hydronium ion, so both of these two reactions are producing hydronium ion, taking a look at the Ka and the Kw, since Ka is the bigger of the two, H3O plus is produced primarily by that first reaction and not the second. Okay, so that's what we can get out of this. So that means when we're taking a look and trying to figure out the pH of our, this solution, we're going to focus primarily on that first reaction to generate our H3O plus, so that way we can measure the pH of that, and we should be pretty close. Okay, so let's set this up using a nice table. So we're going to use the same reaction. We're going to use reaction number 1 on the top. So HVC reacts with water, is in equilibrium with H3O plus VC minus. So initially the concentration is 0.40 molar. And then we have no concentration of hydronium ion, no concentration of ascorbate ion. Okay. Now the change, this time we don't know what it's going to be at equilibrium. So it's going to be minus X. Same thing with H3O plus, except it's going to be a plus X, and the concentration of ascorbate ion also plus X, because those are our products. So at equilibrium, concentration of ascorbate ion, vitamin C, is going to be 0.40 minus X. Concentration of H3O plus will be plus X. Concentration of ascorbate ion plus X. All right. So if we were to write the acid dissociation expression, Ka, that would be the concentration of H3O plus times the concentration of ascorbate ion divided by the concentration of vitamin C. Or using our expressions, X for the concentration of H3O plus times X, concentration of ascorbate ion, divided by 0.40 minus X. Okay. So if we're going to simplify this expression a little bit, this would be X squared divided by 0.40 minus X is equal to 8.0 times 10 to the minus fifth. Okay. All right. Now, here's the question. At this point, back in the last chapter, we would have started rearranging this and solving using the quadratic formula. Now, there is something to point out. Because we're dealing with 10 to the minus fifth, if you notice in the last problem over here, when the concentration went down, so, the initial concentration was 0.20 molar, and the concentration went down by 0.0040, it did go down. It did make that concentration of vitamin C go down, but very, very slightly. Okay, so what we're going to do is use something called the approximation method or the assumption method. So do you need the quadratic? Well, yeah, you do, but what we're going to do is say that it's reasonable to assume that X is going to be much, much less than 0.40 molar. Okay. And if that's what we're going to do, what approximation can we make at this point, and why can we do it? Well, what we're going to say is that because X is going to be so small, we're going to say that 0.40 minus X, that expression for vitamin C, it's really going to be the same as 0.40. So X is not going to change our value all that much. Okay, so if we go back over here and solve what we've got right there, okay, so we had X squared divided by 0.40 minus X is equal to 8.0 times 10 to the minus fifth. What we're going to do is apply the approximation and say that this denominator, 0.40 minus X, that's really the same as saying 0.40. So what we're going to do is treat this as this. X squared divided by 0.40 is equal to 8.0 times 10 to the minus fifth. So what that does, if we multiply both sides by 0.40, we're going to get that X squared is going to be equal to 8.0 times 10 to the minus fifth times the concentration of the ascorbate ion for acid 0.40, and that value is going to be equal to 3.2 times 10 to the minus fifth. Okay, and if I take the square root of both sides, X is going to be equal to 5.7 times 10 to the minus third molar. Okay, so what I'm saying is that what we just solved for was the concentration of hydronium ion. Concentration of H3O plus is 5.7 times 10 to the minus third molar. And how does this compare to pure water? Well, the concentration of hydronium ion is going to be much, much greater than 10 to the minus 7th molar. So we know that this is definitely an acidic solution. Now, was it reasonable to ignore the water equilibrium? Well, yeah, because again, the concentration of what we just calculated is going to be much, much greater than 10 to the minus 7th. So we know we're good. That this reaction is really going to produce pretty much all of the hydronium ion that we're going to deal with. All right, so now that we know the concentration of hydronium ion, if we solve the pH, so pH is equal to negative log of the concentration of H3O plus, well, now we know the concentration of H3O plus, we pop it into that equation, the pH of this becomes 2.24, okay? Now, what if we had to find the concentration of hydroxide ion, since that's also present, okay? We know this expression, Kw is equal to the concentration of H3O plus times the concentration of hydroxide ion. Now, if we're solving for the concentration of hydroxide ion, that's going to be equal to Kw, which is, again, we know that value, 1.0 times 10 to the minus 14th, divided by the concentration of hydronium ion, which we just solved for. So if we take that value again and pop it down here, and I just drew that arrow too far, sorry about that. So if we take that value and pop it in down yonder, the concentration of hydroxide ion should be 1.75 times 10 to the minus 12th molar. Okay. All right. Now, we need to check the validity of this assumption. Okay. So yeah, we can make this assumption, but we also need to make sure that this is a valid assumption as well. And so what we're going to do is take the x value that we calculated, 5.7 times 10 to the minus 3rd molar, and we're going to divide it against the original concentration, which is 0.40 molar, okay, and multiply this by 100%. All right. So what I want to know is what is the percentage of this acid that actually dissociated, that broke apart? Okay. And so if we take these two values, divide it, and then multiply it by 100%, we get that it's 1.4% dissociated, which is good for us. Now, the reason why I say if it's good is that if this was over 5%, okay, 5% or above, we have to use the quadratic formula. Okay, so even if you start approaching 5, usually that's a pretty good indication that you probably may want to use the quadratic formula just to double check. But yeah, absolutely. If you're 5 and above, you have to use the quadratic formula. Now you might be saying, well, why did you show this back in chapter 15 when we were doing the KCs and all that? Why do we have to use it there? Well, this assumption only works when we're dealing with acids and bases. So this can only work when you're dealing with acids and bases. So when we're dealing with KCs on their own, we have to use the quadratic formula no matter what.